here we are. You're in January, you're having a great time, and I miss you so very much. Realize that I hope this unit goes all right. I hope to be clear in these notes. The hardest thing in this unit is sometimes when we get those double and triple integrals where you're just integrating and integrating and integrating and integrating. It's so easy to make a small mistake and have it cascade down. Don't beat yourself up because you made a small sine error or a sine cosine trig mistake or something like evaluated a power incorrectly, right? There are so many small calculations at every moment along the way. It is completely understandable that you might be making mistakes and having errors. With that said, let's start to define regions. I know you understand the mechanics of how multiple integrals are evaluated, but let's talk about how these regions get built. First, before we get there, rectangular regions, we're just going to show something pretty important here. If you notice, my bounds here are going x equals 0 to x equals 3, y equals 0, or 1 to y equals 2. And if I'm paying attention here, I would see that my y bounds moved here, and my x bounds moved there. So it's going to be my goal to do these two integrals and hopefully show you that I'm allowed to flip the differentials as long as I flip the bounds to match. All right. Here we go from 0 to 3. I'm taking off with y, where I'm going to have a 1/2 x squared y squared. I'm going to evaluate this guy from 1 to 2. Hit the ground running. Don't forget my dx. When I bring this down to the next step, I've got 0 to 3. I'm going to get 4 minus 1. 4 over 2 is 2 minus 1/2. That's 3/2 x squared dx. Integrate this bad boy and get 1/2 x cubed from 0 to 3 is 27 over 2. Beautiful. Again, on this side, repeating the same concept, except starting with x. This is going to be 1/3 x cubed times y, evaluated from 0 to 3, dy. When I plug in that 3, I get 27 over 3 is 9, minus nothing. So now I have this from 1 to 2. This is 9 times y, dy. I am having a brain fart. 9/2 y squared evaluated from 1 to 2. That's going to be 36 over 2 minus 9 over 2. And would you guess? 27 over 2. So the fact that these two things are the same means that I'm allowed to flip those bounds if I need to. And in fact, I sometimes do need to. Sometimes starting dx is terrible. Sometimes starting dy is terrible, and I really just want to flip. And this is called Fubini's theorem, where I messed up the... It's not messed up on your sheet, but it's messed up on my early version. As I'm allowed to flip dy dx to become dx dy as long as I flip those bounds with it. Right. C and D belong to y, which now becomes my outer from C to D. Dx goes from A to B, which is now my inner. This looks really simple, but it definitely gets complicated, and making this decision is a huge part of the first half of this unit. When we get to the back half, hopefully it becomes secondhand as you practice those double and triple integrals, but that's what we're thinking and doing and looking at, is how to set these bounds and how to set these regions. But again, let's take a moment and understand what double integral does. All right, my first way to consider is I have the roof of this thing is called my function of x and y. It comes out in terms of z, or height. So at any x, y coordinate, I would get a height back. And so what we do when we have a double integral is I'm trying to find just this cross-section's area. Well, if I want to find this cross-section's area, I would use an integral. And that integral in this case is going to go from this bound C to this bound D. And I'm just going to move my y values here from C to D, dy. And my heights, right, all my little rectangles coming here, all of my heights are going to be based on f of x, y. But again, I'm not really plugging in x so much as I'm plugging in y, and x is staying constant for this one moment. Well then, if that's just one cross-section of my box, if I want to find the integral of the whole box, I'm then going to take this and I'm going to sweep it across the whole x domain. I'm going to drag this rectangle up here as it grows and drag this rectangle down here as it shrinks. And all along the way, I'm going to be infinitely summing that value. Just to show you, my volume here is going to be the integral from A to B of this area. So it's like I'm going to be taking this and plugging it in here. And that's how we get our final double integral. Just to generalize it across any region, to double integrate this multivariate function dA, the differential of the area as it goes across the region, that's going to be my volume. And my volume is going to be, as we said, from A to B, A of x dx, again taking that area and sweeping it across the volume area, sweeping it across the 3D shape as it grows and shrinks. Or we could view this as our double integral. My double integral, my first one, my outer is going to go from A to B dx. My inner is going to be this guy, C to D, f of x, y, dy. That mistake cost me a little bit of space. Again, the inside here that I kind of ran out of space writing. All right. We could do it again in the other direction. This is that same concept of Fubini's theorem, the same shape, but now I'm taking that area. I'm holding y constant, so my area of y is going to be the integral, and again, it's going to go from A to B, where x changes, and the outputs are going to be the heights. I'm going to have all my rectangles going this way. Then I'm going to take this slice and I'm going to move it across this as it grows and shrinks, as my dimensions grow and shrink. I'm going to integrate A sub y from C to D, from left to right. And out is going to come the volume. As I add up area plus area plus area plus area infinitely, I will get out a volume. And once again, I'm allowed to write that volume in the same kind of way. I'm going to not write as much this time. I want to be careful. My inner is going to be A, P, f of x, y, dx. Then I'm going to slap on the outer, dy from C to D. We'll talk about how we make the decision, which one is the inner and which one's the outer, as we get into the next lesson. For this one, we're just crushing examples. You'll see this format often. This is just saying 0 is less than or equal to x is less than or equal to 2. 1 is less than or equal to y is less than or equal to 2.
Attention seniors, at this time,
Everybody loves announcements. Here we go. So now that I know this, I look at this function and I don't think it's a huge deal because it's a rectangular region. We're not really worried about which one we put first or second. As we kind of learned, it should be about the same. When I see this, it's just a straight up function. It's subtraction. I don't have to worry about U subs or fancy integrating techniques. I'm just going to plug and chug. So I'm going to set my y bounds to be the outer bounds just because. I'm going to set my x bounds to be the inner bounds just because. Making sure my my differentials match up with my bounds. Now we can just start running with our calculus. Don't forget, this will turn into negative 3xy squared. It's actually kind of nicer that I put the 0 first because it's going to make my terms a little bit less complicated as I turn the corner here. dy somewhere in here. It's going to be 4, that's going to be 2 minus 6y squared dy. And again, that's an easy integral in itself. 2y minus 2y cubed from 1 to 2. And evaluate this guy. It's going to be 4 minus 16 a minus 2 minus 2, that's 0. So my final answer is negative 12. All right, keeping on, looking at these bounds, looking at another integral. I see this one has this sine function. So if I carried on, just hypothetically, if I carried on over here with y as my inner first integral, we'd see something happen. Y times sine x y. Like, again, this is no different than integrating x sine 3x. Like, as much as I'd like to u sub or something, there's just nothing to do. Like, I can't just, the du is not going to cancel out this. I have to go by parts, probably, to get this thing to turn out. And you want to do a double integral by parts carrying x as a constant? I don't think so. You know what I mean? Like, I definitely do not want to start dy dx. I definitely want to switch these. So I start with my dx, so I'm integrating instead sine for y. Much easier. I'm sorry. Did I lose my mind out here? Right. Sorry, I'm getting caught up on this, but it's much easier to integrate this, right? My constants on the outside, I don't have a function times a function. I'm not mixing types. This should work out nicely, so let's do that. Let's start with our dx first and do our dy second. dy goes from 0 to pi. Dx goes from 1 to 2. I've got y sine x y dx dy. And actually, the way this works is, right, my u sub here, 4x would be equal to u. 4 dx is equal to du. Dx is 1/4 du. So what would come out of here would be 1 over y. My anti-chain rule would make this a 1 over y times y. Negative cosine xy. Evaluated from 1 to 2 dy. I show this extra step just to show, hey, this comes here. Antiderivative of the outside, antiderivative of the inside will simplify. And we're off to the races again, plugging in some values here from 0 to pi. I've got negative cosine 2y plus cosine of y dy. Again, nice, clean integrals, no by parts, none of this yucky crap that the dy dx would have caused. And again, as I anti-chain rule here, negative 1/2 sine 2y plus sine y, evaluated from 0 to pi. And guess what? Sine of 2 pi is 0, sine of pi is 0, sine of 2 times 0 is 0, sine of y is 0. This just is 0. Let's pause for a moment and look at what this region looks like in Desmos 3D so you can kind of understand why the integral might be 0. If I added up all the heights, why they might make 0. For fear of scaring you, this is what it is. Right, you can kind of see these sine waves appearing. You can see the bend as I leave. Right, I have some asymptote looking things. I have some impossible values. Half of it is above, half of it is below. Right, this is just a mess of noodles. But you can definitely see that if I were to add up in a square region, I might have an equal amount above and below, and those might cancel each other out. Even if it's from 1 to 2, the fact that the y's do this, we're going to get some cancellation. And it ends up being 0. On to our last example down here. Find the volume of this solid bound by this thing and this in octant 1. This is our first chance to really start to define some of these bounds. Again, if I'm in octant 1, that means it's in positive, positive, positive coordinates. And so I'm looking from 0 to 2. It's almost like I'm looking at this block, right? Where x goes from 0 to 2 and y goes from 0 to 2. But again, it's this shape, but just inside that region. This will be a really interesting one to look at when we get over to Desmos in just a moment. Let's do this double integral, 0 to 2, 0 to 2. of this function. But again, this function is not quite right. I want it to be a function of x and y, so it outputs z. So I need to make this z equals 16 minus x squared minus 2y squared. That's how easy it is to flip from a multivariate function, a 3-variable function, to a 2-variable function with another output. These become, where here it looks like it's independent, independent, independent. Over here I can see dependent, independent, independent. I'll throw in this function. Again, my choice, dx dy, is not going to matter so much. I don't have much multiplication. I don't have mixing of function types. It's just simple subtraction and polynomial. So I'm just going to go dx dy because that's my preferred order. Again, doing a nice antiderivative here. This becomes 16x. This becomes minus 1/3 x cubed. This becomes minus 2x y squared. This is always the one that I know people are going to forget because you're forgetting that this is part of that 16 constant term, so it gets a linear x on it. Evaluated from 0 to 2 dy. 32 minus 8/3 minus 4y squared dy. And honestly, as much as I'd like to, I'm probably just going to leave it like this. I mean, I can find the common denominator. I can get 96 minus 8/3 or whatever it ends up being. But it's not all that nice. Let's do that. That makes 88/3. So now I'm going to have 88/3 from 0 to 2 minus 4y squared dy. That's going to make 88 over 3y minus 4/3 y cubed 0 to 2. When I plug into, I'm going to get 176 over 3 minus, that's 832 over 3, and 0, and 0. So my final answer is 144 over 3, which is 48. Working off the page because I'm getting so excited on this. Alright, hopefully you can pause and catch up in case I lost you a little bit. Sorry about that. I should do better, especially on my first January video. What am I doing, y'all? Again, let's look at this shape in Desmos 3D. Alright, this is our shape, like kind of a pill shape as I look around it. I'm not surprised. It's an ellipse in XY. It's an ellipse in YZ. But on XZ, it's going to be a circle because they have the same coefficient on the front. So that's kind of the shape we're looking at here as I snap to. But I want to look at those bounds, though. Here are those X bounds. One of them turned gray, which kind of stinks. But there are my Y bounds. And so I'm just looking above this. Right? I've just sliced out this rectangle from 0 to 2. It's bound in this first octant here, just from 0 to 2. And so now when I superimpose, we're just taking the volume of the shape in this shell. Right? Everything from this dome down to the floor. So this whole slice, everything between the blue wall and the gray wall. I hope this helped and didn't make it more confusing that this was the volume we were taking. Alright folks, that's what I had for you today. Have a lovely one. Hopefully this wasn't such a bad first start to January.